My gosh, stop, don't say that. It's so, but what? Yeah, like, the titration. Okay, so give me a second because what happens is we didn't have any comments with the burners. Oh, so what happened is the temperature got to the left of burner and it got brown. So the indicator should be here. Yeah, I was like, I think this is not change. So we said. This is and doing what I'm gonna talk about in this. Basically, I just did the amount of. Yeah. Was comes off and more. Yeah. I just really made me. And money in the wrong places. So that first thing with the CPS, it was like looking at all the information. It said being like on wall. Oh. I don't know. I feel sleuth like dedication. No. But I actually had a hard time finding the board that was all about something. I didn't want to. Oh, HEB. You know what's crazy? And I didn't realize HEB was a legal thing. And so when I went in the Midwest, I was yeah, HEB. And I'm like, no, we've never heard of it. I think that's all audacity to say like, oh no, we thought exactly. It's a little for. So safety is like also one, but it's a graphic there. Yeah, it's Randall, but like the people call it Safeway. And I was like, that first time when she worked at Safeway, I was like, oh, you have good driving. But she's not groceries.
Okay, so if you have any questions, go ahead and scan the QR code. You can actually post your questions, okay? Oh, I don't know whose key. Yeah, okay, you can leave it up here in case they come back. Okay, well, okay. Whose key is this? Yeah, I'll leave it here.
Yeah, it's same like, yeah, with the low humidity, I think that's great.
And it never applies to the next body. It's going to be. I understand they can give us a whole year.
Oh, sorry, here.
It's
It's an office. a really good basis and then.
Just about learning.
I'm not sure. Yeah, no, a lot of this, like, I still say that from here, can you do it this way? You just like, expecting, but this is actually super recent. I wish I had this.
Oh.
Yeah. Yeah. The first thing, like sound, you understand how he gets things, you can do it online, like these. Because he right, he's not right, this is how you know what's talking is. Okay, so do you know how he gets? Yeah. So then we have to say identify a single then you have to know the problem. And so the font is the wrong thing, so you want to it's your. It's yes, but in this case, this is something you can do, right? You have to just explain everything you ever learned. When you're doing this, like this is the phone, and you're doing it.
All right, so let's get started. Okay. So let's look at some of the questions that you guys have. Okay, the first thing is actually the first question is actually determine whether a buffer is acidic or basic. How to do that? How do you know your buffer is actually acidic or basic? Yeah, check the pH, right? How do you calculate pH of a buffer? HH equation, right? So you actually plug in the things that you have into the HH equation so that you can know its corresponding pH, then you will know it's acidic or basic. Okay. So let's answer to the questions, and we'll go through what the HH equation is, okay, later. Okay, we'll go through the HH equation. Small x approximation, when can you use small x approximation? So if you look into the Hangout for chapter 13, right? So we say when your Ka is very small, which is smaller than 10 to the negative 4, okay, or when your K is actually very big, which is larger than 10 to the 4, right? So those are two conditions you can use small x approximation. Okay, so whoever asks these questions, if you are not quite sure what I'm talking about, go back and check out the, okay, either connect with me, I can actually show where we actually go through those things on the Hangout. Okay, or you can just go back and watch the in-person lectures for chapter 13, where you can actually find those information on Teams. Okay. For the polyporic acid, the Ka1 method always going to be. So all of things will actually be determined experimentally. There's no simple rule to predict what the Ka1, Ka2, Ka3 will be. Okay, so there will be actually a short answer to those questions. Okay, so if you are not satisfied with those answers, then we can connect. Okay, so another thing is actually tomorrow we have midterm 2 office hour, right? So I will be in my office as early as 6 a.m. and I will stay until to 5 p.m. I have a meeting between 10 to 11. Okay, so any other time feel free. Okay, well I have dinner, well lunch from 11 to 12, I guess. Yeah, so any other time, you can feel free to drop by my office. My office is at Fleming 139E, okay, which is on this floor. Okay, you can enter the. It's an office complex. You can enter from the door 137. Okay. All right. So those are the things we want to go through. Okay. And here is actually all the things we want to go through today, right? So For chapter 13 and 14, the number one question when you actually encounter a problem is actually you want to know what kind of solution you have. Okay, so you must know the difference between strong acid, weak acid, strong base, weak base, right? And you should also know the definition of conjugated acid and base pairs. Okay, those are the very simple things that you definitely need to know. Okay. Calculation wise, I pretty much list the most useful equations right here. Okay, so you can see the calculation. We kind of went through this one previously, okay, but these are the fundamental knowledge that you should have. Okay, so pH plus pOH equals 14. I assume by now everybody's actually very familiar with this. Okay, if you have aqueous solution, this is always true. Okay, and then if you have an aqueous solution, okay, you have you know the Ka of a weak acid. You can compute the Kb for its conjugated base using this simple relationship. Ka times Kb equals to Kw, which equals 10 to the negative 14. Okay. Every time when we say P something, for example, pH, pOH, pKa, pKb, okay, let lowercase p represent negative log operation, okay, in a base of 10. All right, so associated with this, okay, this is actually some conceptual things that you should know, right? If you have a larger Ka, okay, if you have larger Ka, then you're going to have a stronger acid, okay? Larger Kb, you're going to have stronger base, okay? However, if the question provides you with pKa or pKb, because that negative log, that negative sign, okay, you want to actually find out the one with the smallest pKa value, it will give you the strongest acid. Smallest pKb value to give you the strongest base. Okay, so those are the kind of things that you need to know. Okay, so this is actually what I wrote here. Another very important thing that we should know is that if you have a weak acid, okay, then it will have its corresponding conjugated base, okay, or vice versa. If you have a weak base, you have a conjugated acid, okay. So the conjugated acid of a weak base will be a weak acid. Everybody follow this? Okay, the conjugated acid of a weak base will be a weak acid. Okay, the conjugated base of a weak acid will be a weak base. Did I say the same thing twice? Okay, you know what I mean. Okay, so those are the things that you should have a clear idea. Okay, if you have a weaker acid, okay, weaker acid, its conjugated base will be stronger. Okay, so this is actually what I'm trying to say here. Okay, if you have a weaker acid, its conjugated base will be a stronger base, but the base will still be a weak base. Okay, you definitely know there's only 7 strong acids, right? HI, HBr, HClO4, HCl, HClO3, H2SO4, HNO3. Those are the only 7 strong acids. All the other acid is weak. Okay. For the base, only the 1A and 2A group, hydroxide or oxides, will be the strong base. Okay, all the other things will be weak. The most famous base, weak base, is amine. Okay, so you want to make sure that you do know how to recognize what amine is. Okay, so those are the things I want to bring up before we actually jump into the calculation. Okay. Oh, there's actually one more thing I did not put here, but I assume everybody know, okay? So if today you have a conjugated acid-base pair, the difference between your conjugated acid-base pair is that the conjugated acid will have one extra proton in the H and also in the 1+ charge. Okay. All right. So with that being said, then next thing is actually all about calculation of the pH, right? So to calculate pH, first you need to know there's only 4 types of solution, 5 type, 1, 2, 3, 4, 5 types solution. Okay. Strong acid, weak acid, strong base, weak base, and buffer. Right? These are the 5 different types of solutions. Okay. Each solution has its own way to calculate pH. Okay. Let's start from the strong acid. Okay. Strong acid is actually the species that's going to dissociate 100% once you throw that species into water. Right? Therefore, the proton concentration will directly equals to the strong acid concentration. Okay. So this is actually what we write here. To calculate pH, what you need to do is actually simply plug into this pH definition, right? The pH equals to negative log of proton concentration. Okay, so that's actually how you calculate the pH of a strong acid solution. Okay. If you have a weak acid solution, then we calculate proton concentration using the weak acid concentration multiply Ka, take the square root of it. Then we can get the proton concentration and plug back into the pH definition. Then you get the pH of your weak acid. Okay. For the strong base and weak base is actually very similar to the strong acid, weak acid, right? The conceptually they're actually equivalent. The only thing they are different is that you need to actually replace your H+ with OH-, right? So we know for a strong base, you can compute your OH- concentration is going to directly equals to the strong base concentration. Okay, once you have that, you can calculate your POH by plugging that definition. Okay, POH is equals to negative log of OH- concentration, right? You need to do one more step to get the pH. Okay, so you need to use this one. pH is going to equal to 14 minus POH to get your pH for the basic solution. Okay. Similarly, if you have a weak base, then you compute your OH- concentration using the weak base concentration times. Okay, here is Kb. Okay, not Ka anymore. Once you do that, you take the square root of that, then you get your OH- concentration, right? And then plug back into the POH definition, and then use pH equals 14 minus POH to get your pH value. Okay, so by now you should be very ready for this type of questions. Okay, these are the questions that you can use this equation to save you a lot of time. Okay, don't do the ice table for this. Okay, there's actually another thing. Okay, the salt. Okay, the soluble salt. Okay, so all these salts, once they dissociate, okay, it's going to generate the cation and the anion. Okay, so the cation is typically acidic. Okay, so those acidic species belongs to the weak acid. So the pH calculation will be the same as the pH, the weak acid solution. Okay, but sometimes it will be neutral. Okay, when the conjugated acid, when the cation is the conjugated acid of a strong base. Okay, typically it's actually just 1A, 2A cations. Okay, and those things will be neutral. Okay, for the anions, typically you're going to have basic solution. Okay, weak base solution, the calculation will be the same as the weak base. Okay, sometimes it will be neutral if the anion is the conjugated base of a strong acid. Okay, so we only 7 strong acid, so its conjugated base will be neutral. Okay, so those are the calculation for the first 4 different type of solution. Okay, the very last one is the buffer, right? So once we have a buffer solution, there's actually only one equation to calculate the pH. Okay, so the pH was computed by two terms. The first term is actually the pKa. The pKa is negative log of your Ka value. Okay, has to be Ka, cannot be Kb. Okay, so the first term is actually pKa. The second term is actually negative log. Then you need to actually know what is the concentration of your acid over conjugate base ratio. Okay, so these are the things that you need to know. Okay, and typically that's actually a part you need to actually always compute when you encounter those questions. Okay. The difficult part is that how do you know you have a buffer? Okay, so this is actually a part that most students actually get confused. Okay, so the way to actually know you have a buffer, okay, I summarize these are the three possibilities. Okay, the first one is actually inside the question, it says, okay, you have species A, species B, and look quite similar. Okay, and if you dive in a little bit, you'll realize they actually conjugated acid and base pair. Okay, so that's actually a very standard formula to have a buffer solution. Okay, we'll go through a few questions like that. Okay. The second one is that you have excess amount of weak acid. Then you add in a lot. Okay, sorry, a small amount of strong base. Okay, so because strong base is going to interact with all different kind of acid, regardless if it's strong or weak, right? So the end result of this is that your strong base will be fully consumed, right? So once it's got fully consumed, what you have is actually part of your weak acid will be consumed by the strong base, and it's going to produce its conjugated base. Okay, so once that happens, inside your solution, you are going to have your conjugated acid base coexist. Okay, and that actually gets you back to the first condition. Okay, right now you have similar amount of acid and base, conjugated acid base coexist inside your solution. Therefore, you're going to have a buffer. Okay. Similarly, if today you have excess weak base, then you add in small amount of acid. Okay, so what it says is okay, I have my conjugated base. I add in some small amount of strong acid. Okay, that strong acid is going to interact with your weak base, and it's going to produce its weak acid. Okay, that weak acid is actually the conjugated acid of your weak base. Okay, therefore, you bring yourself back to the scenario number one again. Therefore, you have a buffer solution. Okay, so those are the concepts that you should actually have, and that's actually how you actually identify you have a buffer solution. Okay, any question for this? This is actually a quick rundown about all the equations that you need to know for chapter 13 and 14. Okay, so let's actually one more thing I probably will add on top of this. Okay, for the weak acid or weak base, we're also talking about a equation called the percent dissociation. Okay, that will define as the proton concentration over your weak acid concentration times 100%. Okay, so let's call the acid percent dissociation. Okay, of course you have the corresponding base percent dissociation, right? And that will be actually your OH minus concentration over your weak base concentration multiply 100%. Okay, so those are the key equations that you definitely need to know. Okay, if you want to do well for the midterm 2. All right, so any question for this? Okay, now then let's go to the review questions then. Okay, question number 1. given the following value of pKa and pKb, select the strongest acid from the one list below. Okay, so we just went through this one, right? So we say if you have a large Ka, you have a stronger acid, right? We also say if you have a smaller pKa, you have stronger acid. Okay, so here you're actually looking for the strongest acid, right? And it lists a lot of pKa value here. So you need to actually select the one with the smallest value, smallest pKa value, right? So if you examine these things, this pKa is 3.37. This one is 8.69. This one is 7.53. Okay. So the strongest acid will be the one with smallest pKa. Therefore, we know the answer is HNO2. Yes. Yeah. Okay.
I did the practice test in the first question. And nothing but PKA is.
Yes, that's actually the things I'm going to say, but you already bring up. Okay. So here you can see there are actually two species. It doesn't give you pKa, right? But you can actually compute the pKa from the pKb, right? Because you know the pKa plus pKb is going to equals 14 as well. Okay, so if you look at this, the pK, if you compute a pKa of let's C5H5N, okay, 14 minus that is 5 point something, close to 6, right? And then the other one is 8 point something, so it's actually pretty big, right? So you know they won't be your answer either. Okay. Everybody fine with this? Okay, so then I'll ask you, who is actually the strongest base? Hmm? So you want to know, okay, so if you just compare these two, then definitely you will say NH2 is actually the stronger base, right? But how about the HBRO? The pK is 8.69, right? What is the corresponding pKb? 5 point something, right? Yeah, so it won't be the strongest one because the NH2 is actually 4.75. All right. Okay, so let's actually the question number 1. Okay, so make sure you have this concept. The smaller the pKa, the stronger the acid. Okay, the smaller the pKb, the stronger the base. All right. Question number 2. What is the OH minus in a solution that have a pH of 12.50? Okay, so this question is basically testing whether you know the definition of pH and pOH, right? So the way I would do it is actually, I know pH plus pOH is going to equals to 14. Therefore, my pOH is going to equals to 14 minus my pH, which is 12.5. They give me a value of 1.5. Okay, so pOH we know is defined as negative log of OH minus concentration, and it's going to equals to 1.5, right? Therefore, I know my OH minus concentration is going to equals to 10 to the negative 1.5. And then once you do that calculation, you should get a value of 0.0316. Okay, so there will be 3.16 times 10 to the negative 2. Okay, so that will be actually your OH minus concentration. Okay, so this again is actually testing whether you know those fundamental definitions. Okay, so any question for this? Okay, next one. Give the conjugated base of HSO4 minus. So give the conjugated base of HSO4 minus. Okay, so this sentence tells you the HSO4 minus, this should be the acid or base. Acid, right? So you know this is actually the acid. And you want to figure out its conjugated base, right? And then we know the difference between the acid and base is that acid has one more proton, right? So that in order to get the conjugated base, all you need to do is actually you want to minus a proton from the original equation, right? So once you do that, you should see that its conjugated base should be SO4, 2 minus. Okay, so another conceptual or definition question. Okay, next. Calculate the pH of 0.5 m solution of ammonia, where the Kb is 1.8 times 10 to the negative 5. Okay, so right now we're actually entering the pH calculation. Okay, so every time when you see this keyword pH, the first question you should ask yourself is like, what kind of solution that you have, right? So what kind of solution do you have? Weak base, right? So I hope this becomes a spontaneous reaction that you have. Okay, weak base, therefore, write out the OH minus concentration. Okay, it's going to equals to square root of your base concentration. What's the value? 0.5, right? Times your Kb, 1.8 times 10 to the negative 5. Okay, make sure you operate your calculator correctly. Okay, so if you do everything properly, you should be able to get your OH minus concentration is going to equals to 0.003. Okay, therefore you can calculate your POH. P is in lowercase. Okay, OH is capital. Negative log 0.003. Okay, and then it's going to give you a value of 2.52. Okay, then you can write out your pH equals to 14 minus your POH equals to 14 minus 2.52. Therefore, you get the value of 11.48. Okay, so that you know your pH equals to 11.48. Okay, so this is actually how you solve these type of questions. Okay, one thing I want to remind everybody is that when you write out the pH, make sure you have a 2 digits beyond the decimal point. Okay, please remember that. Okay, but this is actually how you solve this question. Okay, any questions? No, I hope not. All right. Okay, so question number 5. At a certain temperature, the percent dissociation of an acid, okay? In a 1.63 m solution, what is 10%? Calculate the Ka of this acid, okay? Percent dissociation, okay, we just talked about the equations, right? So this is actually one keyword that you want to know the definition, percent dissociation. And then you want to calculate Ka value of one species, okay? And then you know it is acid, right? So you know this is actually a weak acid solution, right? This weak acid is HClO2, okay? From the description, you know your percent dissociation is 10%, right? That means it's equals to 0.1. Okay. So the next thing you do is actually to write out the definition of percent dissociation. Okay, so we know the percent dissociation is the proton concentration over your weak acid concentration, okay, times 100%. Okay. And then that is actually the definition, right? So how do you actually represent the proton concentration of a weak acid? Right now, you should know your proton concentration of weak acid should be the weak acid concentration times your Ka, right? And take the square root of that. So this is something that you should translate. Okay. And at the denominator, you still have your Ha naught. Okay. So I want to actually reorganize these things. So these things is actually going to equals to the square root of Ka on the top, Ha naught at the bottom. Okay, and everything inside the square root. Okay. And you know this whole thing, if you multiply 100% equals to 10%, right? Which equals to 0.1. Everybody follow this? Any question for this step? No? Yes? How do I go from here to here? This one to here? So you guys are not familiar with this operation? So the A, okay, this is actually interesting. Are you guys familiar with this? Yeah, this is actually the simple calculations. Okay, so I guess another way to think about this is actually this. This may be easier for you to think. The square root is actually 1/2, right? And this is actually this. So this will be A 1/2 minus 1. That give you A negative 1/2. Okay, what it means is actually square root over 1. Okay, so this actually kind of the math that you should know. Okay, but if you don't, it's kind of the things that probably actually make it more clear. Okay. So once we do those operations, this is actually this actual equation you're going to get. Okay. So this question is asking for what? What? No. Right? It tells you the Ka. You want you to calculate Ka, but it tells you the concentration of your weak acid is 1.63. Okay. So this actually tells you your weak acid concentration is 1.63. And you want to calculate the Ka. Okay. So what you do is actually just plug in. So this can be written as the square root of Ka over 1.63 is going to equals 2.1. Okay. What you do next is actually you square on both sides. Okay. So it will be Ka over 1.63 is equals to 0.1 to the second power. Therefore, your Ka is going to equals to 1.63 times 10 to the negative 2. Okay. And this is actually how you get the answer. Okay. But again, the key is actually you should start from the definition, right? Because it tells you the percent dissociation equal to certain percent. Okay. And then once you know the percent dissociation was defined as the photon concentration over the weak acid concentration times 100%, that's actually where you get started, right? And then you also know that to calculate the proton concentration of a weak acid, it should equals to the square root of weak acid concentration times the Ka. Okay. Once you go to this step, then you know you can actually simplify this equation into the square root of Ka over weak acid concentration. Yes. What did I write there? It should be 1.63. Okay. Yeah, I think I made some typo here. This should be 9.56. Okay, which we'll go through that very soon. Okay. Mm-hmm. Mm-hmm, mm-hmm. Yeah, I see what you mean. Okay, so why that is the case, right? It's because this question is actually not well designed. It doesn't actually fulfill the small x approximation. That's actual answer to your question. Okay, but very good point. Okay, but in general, okay, in your midterm two, okay, this will be actually a quick way to figure out your Ka. Yeah, and what I would strongly suggest follow this procedure. Okay, any other questions? Because the dissociation is 10%, right? 10% is equal to 0.1. Oh, it's different thing. Okay. Yeah, but you can go back and check out the which lectures that you also mentioned that to me in the lectures, right? But I forgot which one. Okay, and I have another clarification of that specific questions. Okay, but I guess I cannot do any more explanation at this moment. Okay, but if you have those concerns, you can go back and check out the videos. And if that doesn't satisfy you, bring those questions to me again. I can explain to you again in tomorrow's office hour. Okay. All right. Question number 6. What is the pH of a solution prepared by mixing 50 ml of 0.1 m NH3 and 25 ml 0.1 m NH4Cl? Assuming that the volume of the solution are additive and the Kb of amine is a certain number. Okay. So again, you see the keyword pH shows up again, right? So apparently you want to calculate the pH of this solution. So the number one question is actually you want to ask yourself, what kind of solution do you have? Okay. So what kind? It's a buffer solution. How do you know? Yeah, so you want to actually look at the species, right? So this is actually species number 1. That's species number 2. They look somewhat similar, right? So the NH4Cl, we know once it dissociate, it becomes NH4 plus Cl minus, right? NH4 plus is the conjugated acid of NH3, right? So that means inside your solution, you're going to have a good amount of NH3, a good amount of NH4 plus, and these two are conjugated acid and base pair, right? So this you have less situation, then you're going to have a buffer. Okay. So now you know you have a buffer. You want to calculate pH of a buffer, then you go to the HH equation, right? So HH equation is what? pH equals to pKa minus log. You want to put acid on the top, base at the bottom. Okay. So once you know you want to use HH equation, right? The first thing is what? pKa, right? Do you have the pKa value here? You don't, right? So what do? Divide Kw by Kb.
Oh, yeah.
Okay, so Ka is going to be Kw over Kb. Kw is actually 10 to the negative 14. Kb is 1.8 times 10 to the negative 5. Once you do that calculation, you should be able to get the value of 5.56 times 10 to the negative 10. Okay, so let's set your Ka value. Okay, therefore, your pKa is going to equals to negative log 5.56 times 10 to the negative 10. You're going to get a value of 9.26. Okay, so you know the first term you're going to put in is actually 9.26. Now the next thing you want to actually compute is actually the ratio between your conjugated acid over base, right? So you want to know what is the concentration of that? Okay, so it says you have 50 ml of the base, right? So this is actually the base. That is actually your acid. So the concentration of your base, I put A minus here, is going to equals to the mole of your base, which is 50 ml times 0.1 divided by the total volume, right? Total volume will be 50 plus 25. Okay. Concentration of your acid will equals to 25 times 0.1 divided by 50 plus 25. Okay. The things that you really care about is actually the ratio, right? So you know the acid over base is going to equals to this overlap. Okay, so they will give a value of 1/2, right? I guess I should not jump. Okay, so what you're going to have is 25 times 0.1 divided by 75. That's actually your acid. Base will be 50 times 0.1 divided by 75. Okay, this will cancel out. So you end up with just 1/2. So you know the ratio of your acid over base is just 1/2, right? So the next thing you do is actually you plug this back in right to here. Okay, so that the pH is going to equals to pKa negative log acid over base. Okay, so your pKa is 9.26 minus log 1/2. Okay, so once you do that calculation, you are going to end up with a value of, so this is actually 9.26 plus 0.3 equals to 9.56. Okay, so this is actually how you get the pH of this buffer solution. Okay, the key here is really, can you actually identify with the buffer? Because if you can, then you know to use the HH equation, right? The second thing you need to know is actually, can you actually compute your Ka from Kb? 9.26 plus 0.3. So what's the problem with that?
If you do negative log 1/2, and it shouldn't be like positive 0.3, and then it's 9.26 minus.
So it's negative log acid over base, right? Right. So the whole term is actually positive 0.3, right? So it's actually plus 0.3. Okay, so the second step is really you need to know how to compute the Ka from Kb, so you can actually compute your pKa, right? The third step is actually you need to know how to calculate the ratio between your conjugated acid over base. Okay, so you need to actually calculate the moles of your acid, moles of your base, then you know the ratio between them. Okay, then you plug them all back into the HH equation, then you can get your pH. Okay, so this is actually a logical flow how to solve this type of questions. All right, any questions for this? Okay, so if not, then let's do another one. Okay, calculate the pH when 0.68 gram of C6H5COONA is added to 18 ml of 0.5 m benzoic acid, C6H5COOH. Okay, ignore any change in volume. The Ka value of the benzoic acid is 6.5 times 10 to the negative 5. Okay, keyword here again, pH, right? So pH, once you have pH, it's keyword. The first question you ask yourself is, what kind of solution do you have? Right? So what kind? Buffer, right? How do you know it's buffer? Okay, so by now you should see that this things is actually this, right? C6H5COO minus. Okay. So this species and this species, they are conjugated acid and base pair, right? Since you have the similar amount of conjugated acid and base pair, therefore you know you have a buffer solution. Okay, buffer solution again, HH equation. Okay, pH equals to pKa negative log acid over base. Okay. First term, Ka, do you have Ka in the question? You do, right? So the Ka is 6.5 times 10 to the negative 5, right? Therefore, you know you can compute your pKa. Okay. Then we need to actually focus on the second term, right? So the acid concentration. Okay, so the acid is your C6H5COOH, right? And the mole of your acid will be 0.5 times 18. Okay, that's how many moles you have. Okay. Both the constant volume is actually 18. Okay. Base. Base. Okay, first, you know, it did not give you the concentration, it only give you the weight of your base, right? So the first thing to do is actually to compute the number of mole of the base and then the concentration of the base, right? The mole of the base will be 0.68 divided by the molecular weight is 144.1, then divided by 18, right? That's the concentration of your base. Therefore, when you compute your HA over A minus, it will equals to 0.5 times 18 divided by 18. Bottom one will be 0.68 divided by 144.1 divided by 18. And this will cancels out, okay? And then the things on the top will be, okay, what's the number that I get here? Okay, so once you compute all those things, so I didn't actually compute this number. Okay, I actually plug it in and then compute the overall. So pH is equals to pKa, which is negative log 6.5 times 10 to the negative 5 minus log this whole 10. Okay, when you do that calculation, you should be able to get a value of 3.91. Okay, so I'm sorry I did not actually calculate this number, but that's the overall process. Okay, so again, P is really can actually recognize what kind of solution that you have. All right, so any question for this? Okay, so if not, then let's go to next question. Calculate pH of a solution prepared by adding 20 ml of 0.1 m HCl to 80 ml of buffer that is comprised of 0.25 NH3 and 0.25 NH4Cl. The Kb of lead amine is a certain value. Okay, so what kind of solution do you have? A buffer, right? So how do we calculate pH? HH equation, yes. pH equals to pKa negative log HA over A minus. Okay. Everything is fine? Okay, so I actually like your response. Okay, but there's actually one more thing I feel like everybody missed. Okay, first one, yes, apparently you're actually adding a strong acid into a buffer, right? The first thing you want to consider is that which one is actually the no, concentration is actually another thing. I did not actually worry about that. Okay, the things I want to make sure is actually that I indeed have a buffer. Okay, if I can say I indeed have a buffer, what I mean is that the amount of base inside your buffer must be way more than the strong acid you add in. Okay, if you add in more strong acid than the conjugated base that you have inside your buffer, all you have will be a strong acid solution. Okay, but the acid concentration needs to be actually recalculated. Okay, so the first question is actually you want to actually really know what's the mole of your strong acid and what's the mole of your conjugated base, right? So we can do a very simple calculation. The number of mole of your HCl is 0.1 times 20, right? So that's 2 millimole. The mole of your base in this case is NH3, right? Concentration is 0.25. Volume is actually 80. Okay, so this actually tells you have 20 millimole of a weak base, right? So your strong acid will be fully consumed by your base, right? Once it's actually fully consumed by your base, what are you going to get? The moles of your NH4 plus. Okay, originally you have 0.25 times 80 as well, right? So you also have 20 millimole of the NH4 plus before you add in the acid, before you add in the strong acid. Okay. But right now you know your strong acid, 2 millimole of your strong acid will be fully consumed by your weak base, right? Therefore, you know in the end, the number of mole of your NH3 will equals to 20 minus 2, which is 18 millimole. Once that happens, you're going to have more conjugated acid. It will be 20 plus 2, which is 22 millimole. Okay. So this is actually something that you need to actually get used to it. Okay. When you add a strong acid into a buffer, then you know your weak base will be consumed partially. Okay. Its conjugated acid will increase by a certain amount. Okay. So these are the things that you need to know. Okay. So once you have this, then you can actually compute the conjugated acid-base ratio, right? This will simply equals to acid will be 22, base will be 18. Okay, so you kind of know what to write for your second term in the HH equation. Okay. Now the only thing is actually you just need to figure out the first term, right? So since you don't have Ka provided, you need to compute your Ka using Kw over Kb, which equals to 10 to the negative 14 over 1.8 times 10 to the negative 5. Okay. All right, so it's 5.56 times 10 to the negative 10. All right, so with this, then you can write your pH equals to pKa, which is negative log of 5.56 times 10 to the negative 10, negative log, acid over base, which is 22 over 18. By doing this calculation, you're going to get a final value, pH equals to 9.17. Okay, so this is actually the calculation that you should know. Okay, so far this is probably the most complicated calculation we have, right? So any question for this? Okay, so what would you do if that's the case? It's a good question, right? Let's just do this hypothetical question. Let's say you have, so here we have 20 ml, right? Let's say we have 1 liter, 1,000 ml. Okay. So now you have 1,000 ml of HCl into the buffer. Okay, so if that is the case, you know you need to rewrite this here, replace that 20 with 1,000, right? Therefore, you're going to have 100 millimole, right? So you can see that 100 millimole is actually outweighing than any of the weak acid with base, right? Okay, so still you will be consumed by your weak base. Okay, therefore you know once it got consumed, let me change the color, otherwise we are confusing ourselves. Therefore you know your after interaction, right? This one will only have 100 minus 20, which is 80 millimole. Okay, and then your amine, this one, okay, the mole of your NH3 will be fully consumed, right? So you don't have this. The mole of your NH4 plus will equals to 20 plus 20, right? And that's equal to 40 millimole. Okay. So right now you have what? You have a strong acid and a weak acid coexist inside your solutions, right? So NH4 originally have what? 20 millimole, right? Okay. The base is also 20 millimoles. The base will be consumed by your strong acid. So all your base will be gone, right? And once your base got the proton, okay, it becomes the conjugated acid, right? So this guy will become this guy. That's why I write 20 plus 20. Okay, so conjugated acid base is kind of equilibrium. Okay, one decrease, the other one must be increased. Okay, because the proton is actually play the role here. Okay, everybody see this now? Yeah. Very good question. So what if I add water? Water is actually a very interesting species, right? So what's the pH of water? Everybody know the pH of water is 7, right? What does that mean? The proton concentration inside water is 10 to the -7. Okay, so if today you have acid that produce a proton, its concentration is below than 7, -7, sorry, then water will be actually the dominant species. Okay, then it's not going to affect the pH of your water. All right, yeah, so here is actually a case that I think actually nicely actually summarize many of the concepts. Okay, you're adding a strong acid. Okay, then you consume all the, you're adding actually excess amount of strong acid. It's going to consume the weak base completely, right? So all your weak base converted into its conjugated acid. Okay, that's why we put 20 plus 20 for the NH4 plus, right? So now you have strong acid and weak acid coexist inside your solution. Okay, who is going to determine the concentration, the pH of the solution? The strong acid. Okay, because strong acid is going to dissociate 100%, weak acid is actually only going to dissociate a little bit. Okay, so when you are going to calculate the pH of this solution, all you need to know is actually what is the concentration of your strong acid. Okay, so how do you calculate the strong acid concentration, which HCl concentration will be, you know, the mole is 80 millimole, right? What's the total volume? It's 1000 plus 80, right? 1000 plus 80. Okay, so if you do that calculation, what is that number? 0.074. Okay, so this will equals to your proton concentration. Okay, because strong acid, right? 100% dissociate. That concentration will give you the proton concentration. The pH will simply equals to negative log of 0.074, which is going to give you a value of 1 point something, 1.13. Okay, so you need to know what is the solution that you have. Okay, and then based on the equation we give you for those 5 different solutions to compute the corresponding pH. All right, so any questions? Okay, so if not, okay, we don't have too much time left. Okay, I want to actually finish as many as I can. Okay, next one. Determine the volume in ml of 0.71 m KOH needed to reach half equivalence point in the titration of this. Okay, so keyword titration, right? So every time when we say titration, the first thing you do is what? Find out who is actually your titrant, who is your analyte, right? The titrant is what? KOH, right? The way you know is because the titrant can only be strong acid or strong base, right? So apparently right now, the only things KOH is actually the strong base here, right? Analyte will be HClO, which is actually a weak acid, right? So let's actually the first step. Second step is to determine the equivalence point, right? The way you figure out equivalence point is that you use the concentration of your titrant times the volume of equivalence point is going to equal to the concentration of your analyte times the volume of your analyte. Okay, concentration of titrant is what? 0.781, right? VEP is actually the one you are looking for. Concentration of your analyte is 0.494. Volume of your analyte is 49.8. So by doing that, you know your VEP is simply equals to 0.494 times 49.8 divided by 0.781, which give you a value of 31.44 96. Okay, so let's actually the equivalence point, right? If you read the question, it's actually asking you for the half equivalence point, right? So the half, okay, we call it V half, or equals to VEP divided by 2, which equals to 31.4496 divided by 2. That's going to give you a answer of 15.7. Okay. So that's actually the answer you're actually looking for. Okay, any questions for this? If you don't have a question for this, okay, I have a question for you. Okay, if you are actually at half equivalence point, okay, which is at zone 2, right? What kind of solution do you have? A buffer solution, right? If I ask you to calculate pH of these things, can you calculate it? Buffer, HH equations, right? So pH equals to pKa negative log weak acid over its conjugated base. Okay, so you know how to calculate the pH of these solutions, right? Do you have a Ka? You do, right? So you know how to calculate the first term, right? Second term, what is the concentration of acid over base? It's very interesting question. Okay, this is actually, if you think through it, it becomes super easy. Okay, so what does it mean by equivalence point? You have the same amount of titrant and analyte, right? So in the beginning, you have all weak acid. Okay, once you hit your equivalence point, all the weak acid will be consumed by your titrant, right? So all you have will be its conjugated base, right? So in that case, your A minus, okay, concentration can be computed. Okay, but here, where are we? We are at a half equivalence point, right? That means half of your weak acid will be consumed for what it produces. The same amount of its conjugated base, right? So that means it's actually your weak acid over its conjugated base, the ratio will be 1:1, right? So since the ratio is actually 1:1, the negative log of left 1 is going to give you a value of 0, right? So the pH will simply equal to your pKa. Okay, so at half equivalence point, pH is going to equal to pKa. Okay, so this is actually something extra that we did not really emphasize in the past, but I think now it's a good time for you to know. Okay. All right, so let's actually how you solve question number 9. Okay, number 10. Okay, so this is actually more conceptual thing, so let's actually know much computation you need to do. Okay, so let's read through this. Aniline has a Kb of this value. Okay, if every time when I see this sentence, the things I will write is actually the aniline is actually a weak base, right? A weak base, okay, if 100 ml of 0.5 N aqueous aniline solution is mixed with 100 ml of 0.5 M of hydrochloric acid. What's hydrochloric acid? Strong acid, good, okay. And it asks you, is the pH going to be larger than 7, equal to 7, or smaller than 7? Okay, so we know you have a weak base, right? Plus a strong acid. This is going to produce what? It's conjugated acid, right? So you have a weak base inter with a strong acid H plus that's going to produce the conjugated acid. of the weak base, right? So then you look at the amount, 100 mil, 0.5 m, 100 mil, 0.5 m. That means actually what? The same amount, right? So they are going to consume each other, right? So all the weak base will be consumed by less strong acid, right? Therefore, all you have inside your solution will be a full of conjugated acid, right? So it's actually a acidic solution. This is actually acidic solution. Therefore, the pH will be less than 7. Okay, so the answer is actually less than 7. Okay, so let's actually trying to test you. Okay, do you have the concept that if you have a weak base interact with a strong acid, it's going to generate its conjugated acid of the weak base. Okay, if you add in the same amount of weak acid and weak base and strong acid, they are going to consume fully with each other and produce only the conjugated acid on the other side. Okay, and since you have a weak acid in your solution, therefore the pH will be lower than 7. Okay, so that's how you solve number 10. Okay. Calculate pH of 0.5 m solution of sodium acetate. The Ka of the acid is 1.8 times 10 to the negative 5. Okay. So the key thing here is actually to know what kind of solution you have, right? This one is going to dissociate, produce Na plus and CH3COO minus. Okay. So let's take the first step that you should know. Okay. Then you need to ask yourself, what kind of solution do you have? So the Na plus, Na is 1A group, right? So it's going to be neutral, right? Na is actually neutral, right? How about this? Basic, right? So you have a weak base here. So you have a weak base solution, right? Therefore, OH minus equals to the square root of weak base concentration 0.5 m times Kb, right? Because right now you can compute the OH minus. So Kb, do you have Kb? You have Ka, right? So you want to do the Kw over Ka. Okay. So that's 0.5 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5. After all those calculations, then you are going to get the value of 1.67 times 10 to the negative 5. Therefore, you know the POH is equals to negative log 1.67 times 10 to the negative 5. They're going to give you a value of 4.78. Therefore, your pH equals to 14 minus your POH, which is going to give you 14 minus 4.78. So you should have a value of 9.22. Okay, so this is actually how you solve these questions, right? Again, you have a salt solution. You need to know what is the salt that you have. Okay, then you break apart your salt, and in the visualize and recognize. Okay, your Ka is neutral. Your Na is basic. Therefore, you have a basic solution. Okay, therefore you first need to compute the OH minus concentration using weak base equation. Then you calculate your POH, then the pH. Okay. So I guess I can only go to this one. Okay. The very last one I can go probably is this one. It's actually very similar. Okay. So what is the pH of this solution? Okay. Ammonium bromide. Okay. So this guy, right? When you see this guy, can you actually recognize this is CH3 NH3 plus and then Br minus. Okay, that is actually the first thing that you do, because once you can write out this, you know Br minus is the conjugated base of a strong acid, right? Therefore, it's neutral. This one will be acidic, right? Therefore, you have a weak acid solution. Okay, since I have weak acid solution, proton concentration is equals to the weak acid concentration times your Ka. Okay, weak acid concentration is 0.422. Ka, again, you don't have Ka, right? You have Kb in this case. Therefore, Kw over your Kb. Okay, so once you do that, you're going to get a value. Okay, so once you do the calculation, it's 3.17 times 10 to the negative 6. Okay, therefore your pH equals to negative log 3.17 times 10 to the negative 6. Therefore, you get a value of 5.50. Okay, so it's actually basically the same as the question in the previous one, right? But just the previous one, you have a basic weak base solution, but this one is actually weak acid solution. Okay, so this is actually the things I want to go through. Okay, of course, there's actually one question I did not went through, which is the question number 19. Okay, but it is actually very similar to the one that we say we're adding a strong acid into buffer. Okay, so go back home and try to do this by yourself. It will be the same logic, okay, and then the answer was provided here, okay. So I will stop here, and then good luck with your midterm too. Sure.